Hello folks, and welcome to this lesson on enthalpy definitions. By the end of this lesson, you should be able to write thermochemical equations based on enthalpies of formation, combustion, solution, atomization, and lattice enthalpies. So knowing how much energy a reaction requires to go, or to know how much energy is being released by a reaction, can be really useful. But the thing is, you can't look at a reaction and look at what is involved and automatically figure out or have some kind of calculation to figure out what kind of enthalpy is going on in there. Any kind of values that you're going to use have to be found out by experiment. But considering the fact that there are many different types of reactions that exist, and also all of them are stoichiometric, it's not going to be easy to make a library or a reference of every single type of reaction and which has all of the enthalpy values for every single reaction. Now you will learn about how to take some enthalpic information and glean out information about other reactions, but we need a place to start from somewhere. We need some kind of reference that we're going to be able to use and is going to be useful. And so for that, we have the various definitions that are mentioned in that I can statement. And we are going to go over each one pretty quickly to see what they are about so that you can actually use them later on. So first we're going to look at enthalpy of formation. This one is the most basic one of all of those enthalpy values. This is the one that you're probably going to be finding out, or it's easiest to find the enthalpy of formation for any particular chemical than it is going to be for any other type of reaction. The enthalpy of formation is also referred to as a standard heat of formation, and you're going to notice for every single one of the ones that I'm going to talk about today, they all have the naught. And so that is referring to the fact that it is the standard heat, which means standard conditions, which means 25 degrees Celsius and 100 kilopascals. So the enthalpy of formation is the amount of heat that's absorbed or released when 1 mole of the compound is formed from its elements in their standard states. Now, if we're being technical, with a lot of these values, you're going to see a lot of chemicals which people don't actually make from its elements, but this is sort of a foundational definition type thing. So with all of these enthalpy values, there is always going to be a reaction involved with it, and how you write the reaction is going to be very important as well. So let's take the example of water. We have our liquid water, and so for the enthalpy of formation, your reactants are going to be the elements that make up water, so that'll be hydrogen and oxygen, but it is going to be how they are in their standard states. So both hydrogen and oxygen, when you're looking at those elements in at 25 degrees Celsius in 100 kilopascals, they're both going to be gaseous and they both are going to be diatomic. Now, we do need to balance this, and here we now get into the realm of cases where you will actually find fractions in these balanced chemical equations. And that's because the definition is based on 1 mole of water. So you have to remember that, again, the definition is based on 1 mole of the chemical in question. So when you're balancing it, this is going to have to work out to equal 1 mole of that. So when we do that, this is what we're going to get. So again, fractions are going to be acceptable from this point on, in most cases, depending on what you're trying to use. Now, I bring up the enthalpy of formation for water gas, so water steam, basically, and the states are super important because enthalpy values are going to change if you have different states. It takes energy, or releases energy, to go from state to state, and so therefore states are incredibly important when it comes to anything related to thermochemistry. So here's another example for sodium acetate. Pause the video, see if you can figure it out. And so the equation should look something like this. Now, something else for you to know about enthalpy of formation is the fact that, by definition, any enthalpy of formation of an element in their standard state is going to be 0. So that's basically the baseline, because remember, we can't actually find the absolute enthalpy values of anything. It's always going to be a change. You can only find the change in enthalpy. So by definition, we say that the enthalpy of formation for elements in their standard states, those are all 0. All right, next up is going to be enthalpies of combustion. We have a lot of hydrocarbons. We do a lot of burning of them because it is useful to do and you get a lot of information from them. And so this is also a thing. Now, hopefully it isn't surprising that it's the amount of energy it takes. I say it takes, but typically it's going to be released. The amount of energy released when you're combusting 1 mole of a substance. So again, there's that 1 mole idea for the enthalpy of combustion again. Now, I did mention that a lot of these are going to be, I think pretty much all of them are going to be enthalpies of combustions when you're burning hydrocarbons. So that means your products are going to be carbon dioxide and water. Again, as usual, you're going to assume complete combustion unless there's other issues going on, in which case the situation will tell you. So you have your carbon dioxide and you have your water. States are important, as I pointed out last slide. And so you have to make sure that the states of all of your products are also correct. Carbon dioxide is the obvious one. That one is going to be gas. Water is going to be liquid in these enthalpies of combustion. It may not make sense because if you think you're burning something, you're probably going to be getting water vapor out of it instead of water droplets. But here we go. There's your definition. So try to see if you can figure out what the equation would look like for the combustion of butane. And here you see, once again, we have some fractions in our balanced chemical equation because, by definition, it's 1 mole of your butane. Now, when you look at a reference for enthalpy of combustion, you're just going to see a huge table. It tells you what the hydrocarbon is, and then it just gives you the number. Those references are not going to give you the full reaction because they're going to assume that you can figure out what that whole reaction is going to be. For your enthalpy of solution, it's basically the amount of energy it takes to dissolve 1 mole of a substance into water from solid state. And so basically, if you have something like potassium sulfate, it's going to look something like this. Remember that when you are dissolving an ionic compound, it's going to dissociate into the ions that it's made of. And then make sure you're balancing everything, again, based on 1 mole of the compound in question. These last two are going to be more useful if you're in the IB program, not as useful in general, and so you're not going to see these really in a non-IB course. But we have the enthalpy of atomization, and that's the amount of heat required to form 1 mole of gaseous atoms from an atom in standard state. So these are going to be important with certain other things that you have to do, but basically when you take the stuff in standard state and you change them into atoms, that energy is going to be the enthalpy of atomization. Now, in some cases, it's literally going to be as simple as you take solid sodium and you change it into sodium gas. The ones where you have to be careful is if you have something like a diatomic gas. So if you are going to make oxygen atoms, then it is going to be coming from 1/2 of an oxygen gas particle. So if you have diatomic gases, make sure you're being careful there. Otherwise, it should be fairly on the straightforward side. And the last one is lattice enthalpy. It's the amount of energy required to take 1 mole of structural units of a solid ionic lattice into gaseous atoms. So basically, if we're taking calcium chloride as an example, you're taking the solid calcium chloride and 1 unit of that is going to be 1 calcium and 2 chlorine, so CaCl2. And then you're taking it and breaking it up into its atoms, or its ions rather, and so you're going to get Ca2 plus and 2 Cl minuses. So those are your definitions. Keep them in mind as you go through the next lessons because these are going to be quite relevant. So that's the end of this lesson. I'll see you next time.